So, what does a skyscraper in Taipei and the world's longest suspension bridge possibly have in common? Well, they're both held up by a secret, something hidden deep inside their steel. And today, we're going to uncover that beautiful microscopic structure that makes some of our most incredible engineering feats a reality.
To really get our heads around this, we have to start with a massive, real-world puzzle. I'm talking about a challenge of physics, gravity, and just some mind-boggling forces that engineers had to figure out how to solve.
All right, picture this the Taipei 101 Tower. To stop it from swaying in high winds or during an earthquake, engineers hung a massive 90-ton steel ball near the top. But just stop and think about that for a second. What kind of material could you possibly trust to hold that much weight day in and day out for decades? The solution here isn't just about brute strength, it's about elegance on a microscopic level. The answer is found in a very special kind of steel, one with an internal architecture that's as intricate as it is powerful. Okay, so the hero of our story, for such a tough material, has a surprisingly delicate name, perlite. And once you see what it looks like, you'll totally understand why. When you look at it under a microscope, the structure literally shimmers with these iridescent colors, a lot like mother of pearl. And this isn't some kind of additive or a coating. No, this is the actual structure of the steel itself, formed by two totally different materials growing together in this kind of perfect microscopic teamwork. For a long time, when scientists were just looking at two-dimensional slices like this one, they figured it was pretty simple. It looked like a basic stack of alternating layers, a soft one called ferrite, which is basically just iron, and a much harder one called cementite, which is an iron-carbon compound. You know, like a simple layer cake. But is that really the whole story? I mean, if you could actually see it in 3D, would it just be a stack of pancakes? The answer, as you've probably guessed, is no. And the reality is so much cooler. So, how does it really work in 3D? Okay, stick with me on this analogy. Imagine a head of cabbage. All of its leaves are connected together, right? They form one continuous, really complex shape. That's our hard cementite. Now imagine dunking that cabbage into a bucket of water. The water flows into every single nook and cranny, creating a second continuous shape that is perfectly woven into the first. That's our softer ferrite. So when you slice it, yeah, it looks like simple layers, but in reality, it's this single, incredibly intricate, three-dimensional structure called an interpenetrating bicrystal. So who are these two materials, this cabbage and water, that team up to form this incredible power duo? All right, let's meet the team. So on one side, you've got ferrite. It's mostly iron, so it's pretty soft and flexible. That's what gives the material its toughness, its ability to bend without just snapping. Then on the other side, you've got cementite. It's a compound of iron and carbon, and it is incredibly hard. This is where all the raw strength comes from. And when I say hard, I am not kidding. At room temperature, cementite clocks in at around 1,000 on the Vickers hardness scale. Just for context, that's way harder than most other metals. It really is the rigid backbone of this whole structure. The real magic, though, is how they form. As the steel cools down, these soft ferrite crystals start to grow, but they can't hold much carbon, so as they grow, they kind of push the carbon atoms away. And where does that carbon go? It gets immediately soaked up by the growing cementite crystals right next door. It's this beautiful cooperative dance of atoms. Okay, so we have this amazing microscopic structure, but how in the world do we actually harness it to create materials with almost unbelievable strength? Well, the secret is the spacing between those interwoven structures. The closer those leaves of cementite are to each other, the stronger the whole thing becomes. And engineers have a brilliant way to control this. They take a steel rod that's made of 100% perlite and they draw it, basically stretch it, through a series of smaller and smaller holes. This process physically deforms the structure, squeezing those interwoven crystals closer and closer and closer together. And the result, get this, a steel wire with a tensile strength of around 2 gigapascals. To put that into perspective, a single wire, thinner than the lead in a pencil, could support the weight of a large car. This is a perfect example of how tweaking a material's structure at the nanoscale can create world-changing properties that we can see and use. And that brings us full circle. We've gone from the level of individual atoms all the way up to the scale of skyscrapers and megabridges, seeing exactly how the tiniest details create the biggest strengths. Remember those ropes holding up the 90-ton damper in Taipei 101? Yep, They're made of paralytic steel wires, all wound together. And they're not alone. The Akashi Kaiku Bridge in Japan has the longest central span in the world. We're talking almost 2 kilometers, and it's held up entirely by gigantic suspension cables spun from this exact same material. So this is where it all clicks into place. That fine spacing we create through wire drawing, that gives us extreme tensile strength. The combination of tough ferrite and hard cementite, that creates cables that aren't just strong, they're incredibly reliable. And that complex interwoven bicrystal structure is naturally resistant to cracks. The invisible world inside the steel directly enables the visible wonders of our modern world. It really makes you wonder, doesn't it? We figured out how to engineer this incredible strength by understanding a structure that looks like cabbage in water. So, if this one hidden world can hold up our bridges and our skyscrapers, what other invisible architectures are still out there, just waiting for us to discover them and build the future with?